Okay, so in this video, I'm going to briefly talk about damping. So again, in order to derive equation of motion for damped system, we can either use Newton's method or Lagrange's method. But here, I don't want to emphasize a lot on the Newton's method. You can go back to your dynamics class and then check a few examples over there. One thing I want to point out is that the damping force associated with a dashpot or a damper is Fc equal to C times x dot. So that means your damping force is linearly related to your moving velocity, and then that just gives you the amplitude. The direction of Fc is always opposite to velocity. Okay, so that means this damping force actually plays against your motion. Once you remember that, you can easily apply these to the Newton's method. I would like to emphasize the Lagrange's method here. So the same thing, in order to find your Lagrange's expression, we define L equals to T minus U. This is your kinetic energy, and this is your potential energy, right? If you don't remember, you can go back to lecture number 1. So kinetic energy and potential energy. So in mechanical systems, kinetic energy is related to inertial, mass, or J. Potential energy is related to potential energy. It's like either gravity is related to springs or either gravity. So in either case, that means your T and U have nothing to do with your damper. So that means when you calculate these equation on the expression on the left hand side of the equation, you don't have to worry about a damper at all. Just follow your lecture number 1, and then you're gonna find it out. So the damping or the dashpot is only gonna impact what's on the right hand side, Qi. So how can we find Qi? So we need to first find out the Rayleigh dissipation function. So for one dashpot, I'm gonna point it out. Let's say the damping coefficient is C, and then let's say the velocity of the left hand side is V1, and then velocity of the right hand side is V2. So your Rayleigh dissipation function R for this damper is just half C times V1 minus V2 squared. Okay, so that means this term is the relative velocity experienced by the damper. Okay, and then if you have more than one damper in your system, you just lump all these. Let's say this is your damper number 1, and then if you have your damper number 2, then you just find out your R2. No matter how many dampers you have, you just sum the summation of these R functions together. So that's why we have a summation symbol here. So then you find your total Rayleigh dissipation function. So once you have these R, in order to find your Qi, you just need to calculate one more partial derivative. Okay, I think I had a mistake here. So this is to be your Qi. In this case, you just need to calculate partial derivatives for your velocity, and I would say that's absolute velocity. So in the single degree of freedom we're going to talk about in this lecture, we don't have to worry about relative velocity, but once we move to multiple degree of freedom, then the relative velocity comes into play. Just keep this in mind. Alright, so I'm going to use one example here to give you a very quick demonstration of how to use this. So we have a spring mass damper, so we already know that the kinetic energy is half mass times x dot square. The U is half k x squared, and then your L is just T minus U, because we already know these from the previous lecture number 1. So the left hand side, partial L partial x dot dt minus partial L partial x. We can directly write it out. It's mx double dot plus kx, right? So that means when you calculate the left hand side of the Lagrange's method, it has nothing to do with your damping. Just assume the damping doesn't exist and then complete the left hand side. Okay, so for the right hand side, we need to first find the Rayleigh dissipation R. So what is R function? So let's look at this damper here. So on your left hand side is fixed, so that means your V1 is 0. Your right hand side of velocity is x dot, okay, and then your coefficient is c, so your R is half c x dot square. And then in order to find out your Q, is minus partial R partial x dot. Let's go back to here. So this I index here determines, like, that's the ith coordinate. But because again we're talking about only single degree of freedom here, so that means your I is just 1 because we only have one coordinate. So this coordinate is your x here, and then we just need to calculate partial derivative with respect to the velocity of this coordinate, x dot. So cx dot square becomes minus cx dot. So that means your Q is minus cx dot. And then this equation is no longer equal to 0, but equals to Q. So your equation of motion is mx double dot kx equal to minus cx dot. Again, we can move all the unknowns to one side and get the standard format of your equation of motion.